Hello. So this is going to be application number 2 of our what we've learned from up until this point. So first application video, we looked at economics. Now we're going to look at chemistry. Specifically, we're going to look at how we can apply our row reduction techniques to balancing chemical equations. So the example I want to look at is the chemical equation on the board behind me. If you've had chemistry more recently than me, you might recognize that as the chemical equation for propane gas burning. Propane plus oxygen gives us carbon dioxide and water. And so remember sort of the goal with problems like this. I've got a specific number of molecules of propane, oxygen, or O2, carbon dioxide, and water, and I want to pick a number of molecules for each that balances the number of atoms on either side of the chemical equation, right? So like I should start with as many carbon atoms as I end with. I should start with as many oxygen atoms as I end with, and so on. And so what we can do with this is we can actually model this problem as a vector equation. And so, when we start talking about solving equations with multiple variables, that's kind of where linear algebra might start to get involved. And so I want to quickly talk about how we can model a chemical equation like this as a vector equation. So the first thing I'm going to do is each vector is actually going to represent a specific molecule, and each entry in each entry in each vector is going to represent the number of atoms of either carbon, hydrogen, or oxygen that molecule has. So, for example, propane has 3 carbons, 8 hydrogens, and 0 oxygens. Right? So this vector 3, 8, 0 would represent propane. And of course, I'm going to have x1 many propane molecules. And so now I can just do this for the rest of my chemical equation. And notice this vector equation now models this chemical equation where each vector represents the number of atoms contained in each molecule. All right, but remember, to balance this, right, I should begin with as many atoms of each. I should begin with as many atoms as I end with, right? So I should have as many carbon atoms on the left as I do on the right. So in fact, if this is going to be balanced, that is, if we pick x1, x2, x3, x4 that makes everything balance, the left-hand side and the right-hand side of this equation should be equal. And now we've turned it into a vector equation that we just need to solve. But again, it's not quite in a form that we can solve it in yet, right? So ideally, to solve it, we want all of the variables on one side and maybe a constant vector on the left side. So what we're going to do, just like last problem, is we're going to set this up as a homogeneous equation. And so notice what we've done is we've just moved these two vectors to the left-hand side of this equation, and now we've got a homogeneous vector equation. And so remember, any vector equation we know how to solve by just setting up the corresponding augmented matrix and row reducing. And so remember what we can do is we just create a matrix whose columns each correspond to one vector in my equation. And so be very careful here. Notice these entries for the last two vectors should be negative because we're subtracting them. Last column should be 0 because this is a homogeneous equation. And so I suppose that means I should put a little vector sign above the 0 there. And so now we're going to row reduce this. And just for the sake of time, since there's a little more left to do, and I don't want to take all the fun away from you, I will leave the row reduction for the viewers at home. Certainly, if you have questions about row reducing, feel free to email me. I'm happy to send you details. But it isn't a horrible row reduction. So when I row reduced to echelon form, so when I row reduced this matrix, this is the matrix I got. And so now we want to talk about how can we interpret this and what does this tell us about our vector equation. So in order to do this, I'm actually going to erase the original augmented matrix and write more here, since we have our row reduced augmented matrix. So this corresponds to the system of equations that looks like this. And remember, x4 corresponds to the number of water molecules, right? So, looking at question 3, right, asking, do we have any free variables? The answer is yes, right? x4 is a free variable because it does not correspond to a leading one or pivot column in my row-reduced matrix. And so, remember, my way of thinking about free variables, or the way I've talked about free variables a lot, is that we can kind of assign free variables to be whatever we want them to be, right? And so you would interpret them in this sort of an application as, well, I can pick how many water molecules I want to end with, and then everything else will be fixed. And that's actually question 4, right? So I'll quickly jump ahead, answer question 4 on this worksheet, and then I'll go back to the bonus for question 3. Question 4 says if we start with 4 water molecules, then how many of each other molecule are we going to need? Well, and if you just solve each of these 3 equations, you'll be able to calculate that. You'll see we get 1 propane, 5 oxygen or O2, 3 CO2, and then 4 water molecules. And so, of course, we could have picked any ending number of water molecules, and the other 3 variables would have been fixed, right? So that's sort of the idea of free variables. But notice that the way we've got these equations set up, I could actually pre-assign, I guess, so to say, any one of the molecules I wanted to, right? So let's say I knew that I wanted to start with 10 propane molecules. I could just set x1 to 10, and I could still, in a valid way, solve all of these equations. And so notice that just because x4 is the free variable, in a sense, any variable could be free. And so we could actually set this problem up in a different way so that any variable is free by just changing the order, sort of the order in which we assign these columns in our augmented matrix. So it turned out that, because we were going to have 1 free variable, and like the way our algorithm works for row reducing, x4 ended up being our free variable. But I could have actually row reduced so the variable corresponding to propane was free by just sort of rearranging the ways I put my variables into my matrix. You could also resolve all of these equations so that x1 is this variable that pops up 3 times. And so just because water is the free variable here, I could actually assign any of the molecules and just everything would still fit. And so in that way, yes, you could sort of solve for a different free variable. But anyways, that wraps up application number 2 to chemistry. So we have one more application to networks, and then we will be done with section 1.6.